Okay, so it is my pleasure to introduce Massimiliano Rossi, who is now at the University of Florida. He will present us MONI, which is this new idea and very fast tool, I can witness that, for indexing pangenomes. So please, Massimiliano, if you're ready, you can start your presentation.
Hi. Can you hear me? Can you
Perfectly.
see me? Okay, great. Okay, so my name is Massimiliano. So first of all, thank you very much for this very awesome event. And thank you very much for having me here. It's very a pleasure. So my name is Massimiliano Rossi, and so I'm going to talk about MONI, Pangenomic Index for Finding MEMS. So I'm a second-year postdoc at Christina Buscher Lab at the University of Florida, and this is a joint work with Marco Oliva, PhD students in the same lab, Ben Langmead, Travis Gaggi, and Christina Buscher. So since we are at the Pangenomics biohacking, I decided to split my talk into two parts. So in the first part, I will talk about pangenomics, and I will talk about different things that what we have seen so far, because we don't use any graph representation of the pangenome. We use what we call linear pangenomes, which are just the sequences of the genome. So we build a big FM index of these genomes, and I will show you what we can do with that at the moment. And in the second part, I focus on the hacking part. So I will try to talk about more some of the design challenges that we found while building this tool. And okay, let's start. Let's start. Okay, so both I and BWA are listed in Nature's milestone in genomic sequencing for their ability to align millions of reads against one reference genome. Since 2009, there have been an increase of projects, including more and more genetic diversity and increasing the quality of the genomes, like the very recent telomere to telomere project. It would be awesome to use all of them as reference genome. However, BWA and BowTie does not scale. So focusing on short read aligners, we can break them into three main components. So the first component is an index for the reference genome. We have the ability to find seeds and a dynamic programming component to extend the seeds to approximate matching. So in order to scale read alignment to pangenomic level, we need to scale up all those three gears. So I will talk about the first two gears, and I will exclude the third one for this talk because I want to focus on the design challenges. Okay, let's start with the reference genome. So the most famous index for a reference genome is the FM index, which allows fast upstream queries in compressed space. It's composed by the Barrows-Wheeler transform, which is the last column of the matrix of the sorted rotation of the text, and the suffix array, which marks the starting position of each rotation in the original text, sampled at constant distance intervals. So the Barrows-Wheeler transform can be easily stored and used in run length compressed space. The problem of the FM index is that the space for the suffix array sample scales linearly with the length of the text. And it took almost 20 years to overcome this issue by Gaggi et al. That proposed a variation of the FM index called the RIndex, where the number of suffix array samples grows with the number of runs of the BWT. Why do we want that? Because in a pangenome, usually the number of runs of the BWT scales sublinearly in the length of the pangenome. So which means that the more genome we add, the size of the data structure doesn't grow too much. Just to look at it in a bigger scale, so here we have an example of an FM index sampling and an R index sampling. So here, the FM index takes 11 suffix array samples, while the R index takes only 5. Okay. In a series of papers, those authors showed how to build the R index in practical sublinear time and space using a technique called prefix-free parsing. I'm not going to talk about the prefix-free parsing today, but it's really interesting, and you may read it in a lot of paper right now. Okay, so we can now talk about the seeds, because if we have an index, but we cannot get seeds for the alignment, we cannot do much about it. So one of the most famous seeds are maximal exact matches. So we have a pattern and a text, and those are a substring of the pattern that occur in the text that cannot be extended neither on the left nor on the right. For example, ATACA is a mem, because TACA does not occur in the text, and ATACAG does not occur in the text. And the problem is that the RIndex cannot easily find names, but we need to extend it to be able to find them. So, but first we need the concept of matching statistics. So what are the matching statistics? Given a pattern P, basically what we want to do, we want to compute the length of the longest prefix of each suffix of the pattern that occur in the text. For example, the longest prefix of the pattern that occur in the text is TA, because TAT does not occur, and that's length 2. The longest prefix of the second suffix of the pattern that occur in the text is 5, because ATACAG does not occur. And the longest prefix of the sixth suffix is AGAT. Why I highlighted only those? Because those are the mems of the pattern, because we can compute the mems from the matching statistics, from the non-decreasing values of the matching statistics. And now the question is, how can we find the matching statistics? How can we compute the matching statistics using the RIndex? We need the concept of thresholds. So this is how we augment the RIndex to find the mems. Okay, so let's suppose that we want to compute the matching statistics for this pattern, and we have matched this suffix so far, which occurs only once in the text here. And now what we would like to do is we would like to extend this pattern one position before. So we want to include this T, but TACACG does not occur in the text because the only occurrence of ACACG is preceded by a C. So what we would like to do to continue the matching is we would like to find the longest prefix of ACACG that is preceded by a T in the text. And where this longest prefix might be? Well, it might be either in the, it might be a prefix of the preceding suffix, which is preceded by a T, or the following suffix, which is preceded by a T. So in this case, if we compute the longest match, it's ACAC with the preceding one and ACA with the following one. So in this case, we say we jump up and we can continue matching here because we have a T, and we can continue backward searching. Now, let's compute this function for all the suffixes in this interval. So for this second suffix, the longest match is ACA with both the preceding one and the following one. So it's not relevant whether we jump up or jump down to continue the search. And this is true for all those suffixes. This is the interesting one, because now we have that ACAT-GA is the longest prefix with the following suffix, while for the preceding suffix is only ACA. So in this case, we say we jump down because the longest match is this one. Okay, so now you can observe that this function here is monotone. So what we can do is we can just find a position in this interval and say, okay, if my match is above this position I, which we call threshold, we jump up, otherwise we jump down. And we characterize it as we can take any position between the first and the last minimum LCP value in the interval, and of the two consecutive state parameter runs, and we call them a threshold, okay? And we can build it using the same technique, which is called prefix tree parsing, while we build the Barrows-Wheeler transform and the suffix array samples. Okay, so I'm not going to show you how to do that, but now we have an RIndex and we have the threshold and we can find the seeds. So we build this object and that we call the MONI, okay? And we build it against 1 up to 200 complete human genomes from a 1000 genome project. And we compared it against Bowtie, BWA, Puffaliner, and BG. And one thing that we should notice is that, so for building the index for BWA, Bowtie, Puffaliner, and MONI, we use the Fasta file, while for BG, we use the BCI file directly. So we didn't compare the two same inputs, I would say. So the resulting strings are the same, but the format of the input is different. And okay, so for BWA and Bowtie, those were not meant to index collection of human genomes. So after 10 and 20 genomes, they basically either run out of memory, so more than 750 gigabytes of RAM, or they take more than 2 days to build. Puffaliner is the most recent one and run out of memory after 100 complete genomes. VG is the most comparable one. And also here, I would like to point out that we don't need any graph construction first. We can take directly the genomes. We don't need any multiple alignment or any other pre-processing of the genome, okay? And the interesting thing here is that if you look at the size of the final data structure, then we are very close to the size of PG, which it might be interesting also in terms of what is the content of information of the pangenome and what the RIndex can basically store. Okay, so we also did another experiment, which is we took all those genomes that we indexed before and we queried the 600 million reads from the Simon Genome Diversity Project. And what we report here is the number of reads with a mem of minimum of length at least 25, 50, and 75. And what is interesting here is that if you take one reference genome, or if you take 200 reference genome, well, you have 10 million more reads with a mem of length 75, which means better seeds, which means that we can hopefully get a better alignment. And so just to wrap up on the first part, I would say that if you will ever find in a situation where you need linear references, so you don't want to build graphs or things like that, and you want to compute matching statistics of mem, then you can use MONI. And for example, we use the matching statistics to what we can say a child of MONI called SPU-MONI by Ahmed et al. To perform targeted sequencing, for example. Okay, so let's now move on the second part of the talk, which is the hacking part, where we will see some design challenges that we had to face in order to build this big tool. So the first design challenge is about handling all the dependencies of MONI, because MONI is like combination of many pieces of many tools. So, and to show that, I will show you how to build the MONI index. What are all the steps? So the first step is to compute what is called the prefix tree parsing. And so the prefix tree parsing is built using a module of another tool called BWT. And after that, we want to build the BWT, the thresholds, and the suffix array samples. And we use that to do that, we use PFP threshold, which is another component. And then we need random access to the suffix array. So to do that, we use a straight line program, which is built using big repair first, which builds from the prefix tree parsing and a grammar. And then we use shaped SLP. And then the index is of MONI is an RIndex, which combines the two. And it uses an RIndex, SDSLite as a library, and other libraries for querying and also for statistics. That's not all, because all of those all of those modules have dependencies themselves. And this is like the dependency graph of MONI. And it's kind of spaghetti, I would say. And it is led to compile conflicts and issues and all those sort of problems. So I will try to give you an idea of which techniques might be used and what we choose, why we choose that. Okay, the first technique to handle dependencies is the one that I really don't like, which is copy and paste. So basically, we copy and paste part of a library and include it in our library, which can reduce compile conflicts, but it's very difficult to integrate. It's very difficult to maintain. And every fix that is done in the original library has to be propagated manually. And the take-home message here is never do that. That's my opinion, but never do that. The second technique is to use Git submodules, which is easy to integrate and allows to clean separation of project modules. However, the libraries are not common for all the dependencies. So if you have two dependencies that depend on the same library, those two libraries will be different. And so this brings compile conflicts, and it requires recursive clones, which I personally don't like. I want things to be done as easy as possible. The third method is to use external libraries. So those are easy to integrate, and the advantage is that libraries are common for all the dependencies. So you don't have two copies of the same library, and it reduces compile conflicts, but not all the repositories can be installed as a libraries. And many times library requires pseudo privileges to be installed. So, and sometimes they also require strange in CMake compilation arguments. So also, again, they're not the easiest thing on earth. One good compromise is to use CMake external contents, for example, which are easy to integrate, manage dependency conflicts by themselves. So if you have two dependencies that include the same library, the same library will be downloaded only once. It reduces compile conflicts. It does not require sudo. It's the downside is that it takes longer time to compile. You have to recompile all the dependencies, and the same library will be compiled multiple times if you have two different builds of the same project. So what did we choose? Neither of those. What we choose to combine the external libraries and the CMake external content. So how the CMake external content works is that we first declare the target as DSL, for example, the Git repository where to take it. And we can also explicitly identify which exact commit or tag we want. Okay, then we get the properties of this target, and if this target is not populated, we download it. Okay, we can do some configuration first, and then we can add it as a subdirectory in CMake. So basically, you will have all the targets that are built in SDSL available in your project. Now do we combine this with the library method? Well, what we do, we first check whether the library is available or not. If the library is not available, then we download it, then we include it. That's the easiest thing. Okay, so I'm done with the first challenge. I will have to go a little bit faster now, but I hope you can catch up. So I will talk about how we designed the threshold data structure. So to recall, those are position of the minimum LCP value between two consecutive same character brands. So in particular, the first time that you see a character in the BWT, the threshold will be 1. Why? Because if the threshold is 1, then we always jump up to the next occurrence of the character, which is the first one. Okay. So for the first 3 runs, we have the threshold value is 1. For this run now, what we have here in orange is the longest common prefix between this suffix and the previous one. We want to find the minimum LCP value in this interval, and the minimum LCP value in position 3. So the threshold between those two T's has value 3. And now we have a C and a G. Those are both of threshold value 1. And then we have an A. So the A here, we have to find the minimum LCP value in this interval, which is this one, because it's 0. So the threshold value will be 5, and so on. We can compute them all. And what we can observe is that first we have R thresholds, 1 per each run, basically. And that the thresholds are not in the same order as run heads, because, for example, this 3 came before this 1, okay? And that threshold can overlap. Like we have more than one threshold with value 1. So we can store them in correspondence of the second character in the run interval. So we push all those values down and we store them in correspondence of the second character. Now, how do we query them? So some notation, rank AI is the number of A's in the BWT before position I, and BWT select is the number of A's, is the ith A, the position of the ith A in the BWT. So what we do, we want to, starting from position 12, we want to backward search with an A. So what we do, the first thing we do is we get the number of A's in the prefix of the BWT, which is 1 in this case. So given this use 1, what we can do, we can select the next A. Okay, so we can do a select. And given this select, what we can do, we can count the number of runs in which run is this character. This can be easily done with a bit vector marking the run positions. Okay, so we get the seven, that A, this A is in 7th run, so we can access the value of the threshold. Okay, and once we have the value of the threshold, what we can do, we can basically compare the position that we have with the value of the threshold. And if it's smaller, then we just have to jump to the previous A, which is in position I. Okay. And so we update the position I, and then we do an LF step to continue the search. Okay, this is implemented. It works, is quite fast. This distance between is scaled quite well, because from 1 to 200 genomes, it takes only 100 seconds of difference. Okay, but okay, I will try to go fast. We can improve this query by doing some smarter thing, not being naive. What does it mean? It means that instead of querying the BWT, we can query just the string of the run heads. Okay, so as before, we get the rank R, because this will speed up the LF mapping. But what we can do now, we can get directly the position of the threshold by counting the number of runs of A's before this position and counting and selecting the next run head. And this gives us access to the threshold that we can compare, and by basically unfolding the LF mapping, we don't have to recount the number of ranks twice. Okay, so this gives us a little bit of speed up, which is like 1.100 times speed up, just because we disassembled all the building blocks of the RLBWT. The last thing that we did was a succinct representation of the threshold, which basically is the observation that if we divide the threshold per character, then we can represent each threshold for each character as a bit vector, and query them by just counting the number of threshold per character and comparing them with the number of runs in the BWT. So I will skip that. And what it gives us, that it's a little bit slower, as someone may think, but it's also smaller, like those are 6 gig of difference, more or less. Okay, so that's almost it. So I wish to thank all my co-authors, and I would like to thank the members of Burchell Lab, Langmead Lab, and Yegi Lab. Those are the funding agencies. This is the GitHub of MONI if you want to check it out. And this is my contact if you want to ask me questions and other things. Thank you. I ran a little bit late. Sorry for that.
No, thank you very much. It was a very nice talk, and I appreciate also the fact that you have been able to illustrate both the algorithmic part and some part related to the programming aspects of that. So we have a few questions. We start from the first one, which you have already, at least in part, answered, and it is what data is actually stored for MONI.
Okay, so the data that are stored for MONI are, we have a run-length encoded BWT, and then we have the suffix array samples at run boundaries. So which means the suffix array samples, okay. So in this case, we would have a suffix array sample here, 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 and then at this position and at this position. So we skip all of them. And the same for all the other runs. Okay, so like we skip this sample, and so the number of samples is O of R, and the threshold stored either in the big vector position, which are basically R thresholds, and or in the plain version, which is the one that I showed you here. So those are the components that we store, and then we have also a random access data structure, which basically is a grammar that it's a compressed grammar, a straight line program, I would say, that gives us random access to every position of the text, and we need that to compute the mems, because in the first pass of the mem finding algorithm, we compute the position of one occurrence of the mem, and in a second pass, what we do, we use the random access to get exactly the length of the matching statistics. So those are the components, the main components that we store. We also have another small, like I would call it index, but it's not really an index, which keeps tracks of the structure of the Fasta file.
Okay, thanks. Now we have what is probably more an observation than a question. Quick, you had to start with the phased 1000 genome VSF to generate the FASTA from those assemblies, but this is a temporary problem that you won't have when working with an assembly-based pangenome like that from the HPRC. I don't know if you want to comment on that.
Yeah, yeah, this is like, okay, I would say slippery situation, because we have the VCF file. The VCF file were generated by aligning toward the reference genome. Yes, the thing is, we can also now build MONI from directly from the VCF. I don't have showed this yet, but we have modules that can do that. And I don't know exactly about the assemblies of the HPRC, but if I remember correctly, those should be like directly Fasta files, right? So we don't have any problem of generating the Fasta files from any other source. Those should be, if I remember correctly.
Yes, they are Fasta files. That's
yeah.
We have confirmation on the matrix room.
Oh yeah, okay.
Yes, I confirm. Another question.
Oh yeah, sure. I will use that for future testing. Yes.
So, have you considered incorporating BWT tunneling method into MONI?
Not yet. We would like to investigate that.
Excuse me. Maybe you can summarize what BWT tunneling is, because I'm not sure that everybody is aware of that.
Okay, so let me see if I recall it correctly. So basically, the tunneling of the BWT should be when you have two. So basically, you have suffixes that are always grouped together, and you can tunnel those suffixes and basically remove groups of character from the BWT, so the BWT becomes smaller. I think this might be the high level concept of tunneling. So the idea is of tunneling, basically it's you can take the BWT and make it even smaller, and this will help by reducing the size of the BWT. One thing that I want to mention is that, so the run length encoded BWT at the moment, the problem is not the space, but it's more the query time for the querying the run length encoded BWT. That's the main problem. And I don't know about the performances of the tunneling method of the BWT, but I would love to investigate also on this aspect.
Okay, another observation is that downloading library with CMake is fine if you are allowed to download from the internet and in a containerized environment such as GUIX or Nix, that is not always possible.
Mm-hmm.
And so this means architecture is not that easy to be used on Nix or GUIX.
Yeah, okay, that's a fair point. The thing is, what I'm trying to do is to try to give the most way possible to install the tool. Like, this is the easiest way to incorporate the tool in another project. But what I would prefer to do, like use CPAC to generate a deb file and then use the deb file to install it, or to generate the binaries directly, which may help also. So that's not the only way, but I think it's the easiest way for someone that want to use MONI in their tool. So it can integrate MONI in the same way, which will handle all the dependencies. That's my view. It might be opinionable, but fine with that.
Or just a bit of promotion, let's put it this way. You can try to build a GUIX package for MONI, and so everybody will be happy.
Sure.
Just
definitely.
Yeah. And then, so you described some possible conflicts that you have with libraries and programs, and then the fact that you move to CMake and external libraries. How much of that is due to the choice of C++ as the programming language?
Okay, so one thing is because I know it quite well, which is kind of a lazy answer, because there's always room to learn a new language. The other thing is that I think SDSL library is implemented in C++. It also has porting, for example, for Rust. I know that, but and also I kind of feel very comfortable with C++. So it's more like a personal choice rather than different type of choice of why using C++.
Yes, but because I made that question, so I can interpret. What I was meaning actually is how much of your experience can be translated in another programming language. So I mean, if I'm not going to implement that in C++, how much of your lessons that you learned and the solutions you have chosen are sound in even in a different set?
Okay, so for handling the dependencies, that really depends on the programming language that you are going to choose. That's sure. The thing is, if you want to re-implement MONI in another language, you probably have to implement most of the dependencies like the BWT and other things, or at least provide an interface that use them. About the way we design the data structure, that also depends on how the single primitives like rank and select are implemented in the new language. So, for example, so it's almost always true that rank is much faster than select. So a very good rule of thumb is to avoid as much select as possible in your code. Other than that, it really depends on the implementation mostly of the single primitive and like how fast the primitive is with respect to another one. Have I answered the question, or
yes, no, that's fine. That's fine, and it was a very interesting answer. So we have a final question from Massimiliano. Do you know a good resource to learn about RIndex?
So one good resource is I would say the original paper, which okay, my share. I will link the paper in the chat. Which so the original paper is Soda paper in 2018 by Gegi, Preza, and Navarro, in which they basically define phi inverse, and then they extended it to a full compressed suffix tree in O of R space. There is also a good summary, I would say, in the MONI paper, and there are also two very new, so published last year, like surveys on compressed indexing by Gonzalo Navarro that appeared in the ACM journal. I can link them though also in the Matrix channel.
Thank you very much again, because last
thank you.
And I'm seeing that is writing again, so maybe okay. No, if you can link them, it would be great. Okay, so what I was saying is that I'm very happy that we had so many people participating and attending the conference. I'm especially happy that we had so many young researchers and practitioners of the field. There is one